Hello, everyone, and happy holiday season. Welcome to our podcast series on infrastructure repair live. This is our episode 7 in the third season of this podcast. I don't know what time sure flies. So, uh, if today this is the part 2 of a two-part series that we started talking about repair of culverts. And if you remember, the first one that we did about a month or so ago was using the wet layup system as well as the Spire Plus panels. Those are primarily used for box culverts. That's the first group that we covered. And then today our focus is going to be on the second part of it, which is for corrugated metal pipe culverts, as well as, potentially some tunnels or basically any kind of buried pipeline that you have where it is subjected to uh, both, gravity and traffic loads and so on. And in today's presentation, we're going to be looking at a couple of different ways of repairing this. One of them is using the StifPipe, and the other one is using a gunite and wet layup combination. And I have some case studies on both of these, and hopefully this would be of interest to you. So on this first part of it, which we focus on using StifPipe. So this StifPipe is a concept that I came up with about, gosh, almost like 11 years ago. So the idea was that with my structural engineering background, looking at the pipe, I was looking at how can we achieve a stiffness or ring stiffness for a pipe without adding a lot of, an unnecessary cost of adding a lot of layers of carbon. And in fact, the way this whole thing came about, the creation of this StifPipe, was because when we repair pipelines like pressure pipes, usually 1 or 2 layers of carbon is sufficient to take all of the internal pressure rating. But what we have noticed is that, in recent years, a lot of our clients were asking for, let's assume that at some point down the road, the host pipe will totally disintegrate. And so they wanted to have a liner that not only would take the internal pressure, but it would also be stiff enough to take the loads from gravity and traffic above. And as you know, that type of behavior relates to the ring stiffness of the pipe. So there are some of our competitors in the FRP industry. They said, well, we can make a very thick layer of FRP, layer after layer of carbon, but that becomes really expensive and cost prohibitive. So this is why I developed this StifPipe concept. So as I show here in this slide, let's say these green layers that I have here on the first one, there is 2 layers of, let's say, carbon fabric with a total thickness of T, and it has a relative stiffness of 1. Now, if we put some core material between these 2 layers and spread the 2 layers a little bit away from each other, so we get double the thickness, you see that we get 7 times that stiffness. Or if we put it a little bit farther away, we get significantly more, 37 times the stiffness, for example, when you have the total thickness being 40. Now, keep in mind that as we go from the first case to the second and to the third, let's say the more expensive part of this pipe, which is the layers of carbon, they remain the same. But we are just adding a lightweight core material to kind of serve as a web and give us a more rigid structure. So initially, when we were developing these, in terms of what you could use as that web or the core material, one of the products that we have used is this 3D fabric. These 3D fabrics are kind of a unique construction where you have, for example, 2 layers of glass fabric that are connected together with very short fibers of glass. And then the 2 layers, they can be saturated with epoxy together, but as you let the top, as you let them cure, the top layer would rise from the bottom layer, and what you see on the upper right, you get basically two flat plates that are rigid and separated by a series of webs. So that's kind of when we started it. We were making a lot of pipes like that. And over the years now, we have changed that core, and we use different core materials also. But this concept was, in 2016, I received the ASC Innovation Award as the world's first green and sustainable pipe for this StifPipe technology, and we've used this successfully over this last decade on many projects. So let's look at the design of this, but what goes into this. So we basically, when we design this StifPipe, we use the layers of 1 or 2 layers of glass on the inside of it. Those are primarily used to take the internal pressure of the pipe, if you have. And then we use a core material plus potentially some carbon or glass on the outside. Those are primarily intended to provide the rigidity or stiffness, the ring stiffness that we need for the pipe. And the nice thing about this is that, as you'll see, it is very easy to construct this stiff pipe, so it can be made into any shape, including non-circular shapes that are commonly used for either culverts or for sewer pipes as well. So we can use this stiff pipe in 2 different ways. One of them is to make segments of pipe that you can use to slip line a pipe or a culvert for repair. The other one is when you use it in the field to apply it as a wet layup application. So, and we look at both of these together today. So, the typical, similar to design of any pipe, you can calculate like the deflection or the bending stresses and parameters that you need. But really the main difference between, let's say, this stiff pipe and say a typical steel or concrete or other types of polymeric pipes is that the material properties, because this is a composite product made out of many layers, so these factors, for example, like the EI that I show here, these are a little bit more difficult and challenging to obtain for these, because you have to model it as layer by layer. But we do that with using in many cases, we use the finite element analysis to analyze these pipes. So let's say in this case, these are the kind of input that you can have, like, here this is just an example, but let's say in this case, we have like the first layer that you see is the U41C, which is a 41 ounce unidirectional carbon fabric. Then we could have, for that product, we have its mechanical properties like the thickness and modulus of elasticity. And then we may have like a layer of glass that has its properties there. And then you see that 10 millimeter thick core, which goes as the core wall of this. And then we combine these for different designs. For example, we can say how many layers of each of those materials can be put in what location. And based on that, we obtain the mechanical properties or model this with finite element analysis. And then you can, once you have your model built, you can subject it to various stresses, and you get both stresses, strain plots. I won't go into too much detail of that, but that's the way that it can be done. But to obtain some of those mechanical properties, this is really not, you can do it analytically like that, but we also verify these by making samples of this. So for example, what you see in my hand which is actually similar to that sample that you see being tested. So this has a layer of carbon. The black one is a carbon layer on the bottom. Then we have maybe it looks like about a 10, 11 millimeter thick core, in the center of the wall of the pipe, and then another 1 or 2 layer of glass on the top. And then, as you can see, we can subject these to various ASTM tests and get their required mechanical properties. For example, for flexure, done this way. So in some cases, if it is a relatively easy sample, we could test it like a beam. But in some cases where we have a very unique structure like this, one of the projects I'll be talking about is this project we did in Detroit, which was kind of like a world record setting size pipe that we made, 16 foot in diameter. So for those special cases, let's call them, then we can actually make a piece of the pipe and test it in the laboratory. So here we have built an arc of the exact pipe that we were going to be using on the project with the same number of layers exactly as the finished pipe. And then we test it and to get the mechanical properties. And, there's always, we make sure that verify this with finite element methods to make sure that there is a good match between what we are doing in both ways. So, one of the concerns or features of this StifPipe is that it is by far it's the lightest pipe that you'll ever run into. So it has the highest strength to weight ratio of any pipe. So that could potentially in some projects cause issues with buoyancy, especially if you're lining, for example, a culvert, which is full of water, or if it's a sewer pipe that you're lining it and there is flow in the pipe. So this buoyancy causes the pipe to rise, of course, because it is pretty light. So there are ways you have to make sure that, for example, this buoyancy does not cause any damage to the crown portion of the pipe, getting it squeezed against the top of the existing hose pipe or culvert. And but we can take those into account, and you can calculate these by either adding some weight to it to make sure that it kind of floats, but it doesn't go all the way to the top. Of course, this makes it this lightweight of it makes it really easy to install. And then we can also, as a part of the design, during give a schedule of the grouting operations, so we know how much at what level by level in so many lifts you would put the grout between StifPipe and the hose pipe to prevent this kind of rise as a result of buoyancy. So let's look at one of these projects that earlier jobs that we had done in this happens to be in Australia, but the way we make these, especially for smaller diameter pipes like this one, which is about 5 feet or so, you make a mandrel which is made of these telescopic arms. So with these telescopic arms, we can pull the arms to the exact location that we want. And this is in fact why you could make a non-circular pipe, because by pulling some of these, not all of these arms need to come out to the same distance. So you could make it like a oval shape or anything that you want. And then once that mandrel is made in the shape that you wish, you start wrapping various layers of glass or carbon, including, like on the right here, they're putting that core material. So you put all of these, wrap it around the mandrel, and then overnight, this cures in ambient temperature. You don't need to, heat it or anything. And so by the next day, you have a finished pipe. You could collapse the mandrel, pull the finished pipe out, and then repeat the process. So in this particular project in Australia, the length of the culvert that we were repairing was 80 feet long. So we made 4 pieces of these pipes, each of them 20 foot long, to do the whole 80-foot length of the culvert. And as a part of this design, we also provide all of the details of like the number of layers, how they go, how they overlap, whether they are butt jointed or they overlap by whatever distance, including things like the direction of the flow and so on. You don't need to worry about those, but just I wanted you to be aware of it, that these are some of the things that you need to be concerned with, and we do take into account in the design of the pipe. So let's say once you have made the pipe, then in this case, we actually had taken measurements of the collapsed culvert. So the culvert was no longer round, it was partially collapsed. So we took and that's really one of the advantages of this StifPipe, is that you can make it to any size. You are not limited by like 6-inch increments. So we took measurements of the deformed culvert and used that. And based on that measurement, we made a StifPipe that pretty snugly fit into that culvert. So then the pieces are delivered to the job site and they're pushed inside of the culvert, and they're just pushed one after another. And then in this case, for the connecting the pieces together, because it was a large enough pipe that you could have man entry, the joints, for example, this is one way of connecting the joints, is that they would be just flush, and you would somebody would go from inside, apply layers of fabric on the inside of it with wet layup to make it a continuous pipe. There are ways you could put some type of clamps on the outside as well, or connecting them from the outside. So these are one way of connecting them. And I, this, one of the, if you watch the video with this project, which was on the previous slide, you can see the address on YouTube. When you watch it, you notice that one of the advantages of this pipe is that in this, I don't have the video for you to show you, but in our video, you'll see that these 20-foot long pieces, these two guys are just pushing it by hand. And this job was in a very remote site in Australia. So the fact that we didn't have to take any heavy lifting equipment or pushing jacks and so on to that remote site, that reduced the cost significantly. And that's really one of the advantages. In fact, they had, these casters turned upside down. And so the pipe was kind of sitting on the wheels of the casters, and these two guys could push it in place. And that kind of repair, we've done it again on a number of projects in Australia and in US as well. Here are just some samples of how this StifPipe can be used. And until recently, actually, the biggest one that we had done was a 10-foot or 3-meter diameter for a project in Australia. But then more recently, we broke that record with this pipe that we did for a project in Detroit. And this is a 16-foot diameter pipe that we built to repair a 17.5-foot diameter tunnel. So this tunnel was a concrete tunnel that was corroded or deteriorated over the years. And we built these pieces, and they would just get slip lined inside of it. I'll talk more about it in a minute. But this was such a major project that the Composite World magazine had us as their cover story a year and a half or so ago, as being the world's largest pipe that has been made this way. And just to give you a perspective on the size of this pipe, if you clip the wings of a Boeing 737, that fuselage would fit inside of this StifPipe with 4 feet or 1.2 meter of extra room to spare. So it is a pretty big pipe. This is in fact the actual sample of the wall thickness, which is really not, as you see, it's really not that thick. So it's only about 1.9 inch or 48 millimeter for a pipe that is over 16 feet or like 4.8 meter in diameter. So, but here, because we needed to achieve this bigger thickness, then we used 2 layers of core, 10 millimeter each, and then various layers of carbon and glass, added to give you the rigidity that we need. Now, in this case, actually, because of the large size of the pipe, you couldn't go around the mandrel or by hand reach to put the layers of fabric around the mandrel. So here we mounted the mandrel at the manufacturing facility on a rotating motor, And so as that is rotating, just the layers are being added, and the fellows who are making it, they're just standing stationary, but they just add the layers and resin to it as the pipe kind of turns on that mandrel. So here are the finished pipes. I say on-site manufactured, or it is near-site manufactured, because these are really, they can be made on-site also. If you don't need a lot of that's one of the beauties of these technologies, that you could make it. So, if any of our audience are listening or watching this from any other country, these pipes will be made close to the job site in your country. They don't need to be made in any particular big factory or facility manufacturing plant. So here are a bunch of these, as you see, ready to get shipped to the job site. And by the way we ship these, we designed these to be 14-foot long, because along the short distance from this manufacturing facility to the job site, there were some bridges that the trucks had to go under those bridges. So these lowboy trucks are about 1 foot off of the ground. And so then we have 14 foot of height or the length of the stiff pipe, total of 15 feet. And the lowest bridge that we had had a 15.5-foot clearance along the way. So that worked really nicely. And as you see, we put 2 of those side by, vertically standing for transportation. Okay, so there are, different aspects of these projects that, we take care of to make sure that you get the good quality that you want. One way would be an inspection log of all of the, part components, the lot numbers of all of the resins and fabrics that go into building the pipe, and the locations, and each piece is numbered so we know where it goes. So there's a pretty good accurate recording of that, as well as other things like checking the surface of it or checking for any anomalies, so that when the pipe leaves our hands and gets delivered to the client, it's all of those things are taken care of. And one of the things that we developed, for that Detroit project was an ultrasonic non-destructive technique that we developed in collaboration with some of my former colleagues at the University of Arizona. And so in the middle here, we were doing kind of calibration of this to make sure that the system works with that arc panel that you saw. We were testing it before, so we are now testing it for ultrasonic in the lab. And then in the field, actually, every piece of pipe that was completed, we would do this ultrasonic testing on the pipe. And this would, find if there were, for example, any minor voids that needed to be filled and corrected, before the pipe was delivered. So it is it provides you a certain, good assurance that the pipe is in good shape when it is delivered to the client. Another aspect of it is the joints that, to make sure that, for example, your joints are fitted. Now, the project that we did in Australia, you notice we were wrapping it with wet layup. This particular project, the joints were a bell and spigot joint with a gasket. So in the manufacturing plant, we connect them together to make sure that they are nicely fit. And you can see this is a pair of them, and on the right is that connection, the joint location, which is pretty nice and smooth. Now, in this project, so for installation of this one, it was kind of unique. They built a shaft. The contractor built a shaft, and then the top portion of this tunnel was removed and the pipe pieces were going in. And they actually had this special equipment. It's a pipe carrier or pipe mover that they put that inside of the tunnel. And then as the pipe segments were put in, this would grab them and push them in. And I think I have a couple of these videos that made the pipe segments going inside of the pipe as they're being lowered. And let's see. Okay, this is inside of the pipe. You can see that they use that pipe where they go inside the middle of the pipe and then they push it. So these then get pushed to the previously installed pipe. They get connected, and then the next one is lowered, and the same one after another. They go out inside of the pipe. So it is a pretty unique way of doing it. And this one just shows you the tunnel itself, so you have an idea of how big this tunnel is. So and I thought I'd just tell you that because you may be looking at the same thing for some of your projects, various options that you may have. So in this project, a engineer of record had identified 3 different lining systems for this tunnel. So one of them was channel line, which was made in United Arab Emirates. The other one was a polymer concrete. Both of these were delivered in short pieces that the contractor on the job site had to connect together like a puzzle to make a pipe out of it. And especially when you get to these large diameter pipes, it becomes very challenging and time consuming. But this StifPipe was the only one that was delivered in fully, completed pipe like you see here. And this is the job site, and right behind here you see the top of that tunnel, that the shaft rather, that that they lower the pipes in. And there is on that back is that pipe moving equipment is sitting there. And here on the right you see a couple of the pipe segments from channel line that they came in pieces. So if you look at all of these different systems, as far as the length of these products, you can see that our StifPipe, we made it 14 feet long, and we could have made it longer, but just as I mentioned, because of those traffic restrictions, we made it that length. All of these other channel line was only about 7.2 feet long, and the other polymer concrete was 6 foot. And then the wall thicknesses, again, when you look at, here with the StifPipe is less than 2 inches, the other ones are significantly more. And the weight of these per foot of the length of the pipe, we have, this is StifPipe was 570, channel line is 1,800 pounds per foot, and the other one is over 3,000 pounds per foot. So all of these add to the speed of installation, of course, and as a result, this StifPipe, the contractor managed to install about 200 feet of it per month, whereas with the other ones were either half or this, significantly less in production time. Now, the other thing that I wanted to, kind of like a different method I want to discuss briefly. This is, I don't have a Culvert example, but this could be exactly for Culvert as well. This particular job was in Phoenix outside of a Starbucks coffee shop. It is an underground stormwater retention system. So in this case, this was in the parking lot. It was about 5 feet below grade and has a diameter of 8 feet. And the length of it, which is about 77 feet. And you can see, because they always, water goes inside of these, and then, of course, they evaporates or they discharge it, and it just corrodes after a while. And this was also designed for HS20 loading. But what here is a cross section of basically the pipe, so 8 foot diameter. So the way we designed this, because most of the damage was in the lower portion of it, as is often the case with even some of the culverts that you run into. So in this case, we strengthened the lower portion of it, but we did extend it a little bit past that and used these shear connectors to make sure that you have good load transfer between the new concrete ring that we put and the old corrugated metal pipe. So in this picture, you see here that these are the connector elements, or like those shear tabs are there. You can see them, and then the wire mesh has been added. Then we apply gunite to it, or shotcrete, to make that about a 3-inch thick layer of concrete near the bottom that tapers to the as you get to the spring line. And then the entire repaired area, we covered it with this a layer of glass FRP. And the function of this glass FRP is that in addition to providing some strength, now you have created an impervious layer that keeps this culvert or pipe from future corrosion. So that's the way this was done, and you can do the same thing in some of the culverts. It's a very similar approach. In case you have some cases where the tunnel or the, it won't be probably for a culvert, but if the tunnel is very deep and you cannot slip line it, one of the ways is also to build a 3D like StifPipe inside of the tunnel, using the host tunnel as basically as your like mold. So this was a project. You can see the video link, you can watch it. This was a tunnel that we repaired a few years ago under in the downtown of Minneapolis in Minnesota under I-35, and the tunnel was about 150 feet or 45 meters below grade, and only a piece of it, which was about 20 foot long, was very severely deteriorated. So we took all of the material down a shaft, and then the crew took it to this location of the repair and applied it layer after layer to build this fully structural liner. This tunnel itself was 12 foot in diameter, and the thickness of the StifPipe that we built on it, it was about 1.5 inches or so. Of course, in this case, because we are building the StifPipe directly on the surface of the pipe or tunnel, there is no annular space, so you don't need to worry about any grout injection or anything like that. And then the last thing that I want to show you is this little video. This is a kind of a unique way. It's not perhaps for a very long-term solution, but if you have a culvert that is leaking and you want to do a quick fix for it, let's watch this quick video together that you see how this works. So we make these laminates that you can take any length of it that you want and make a coil out of it. And once it is put inside of the deteriorated culvert, when you release it, it snaps in place, and you could put some epoxy in between. So now it snaps, and you basically have created a continuous pipe inside of your deteriorated culvert. And as long as you seal the edges of it, then water can flow in here and you would not have any infiltration or exfiltration from this. So it's definitely a good quick fix for some of these types of applications if you have. So with that, I kind of come to the end of this one. I just want to add a couple of housekeeping notes. Please remember that all of our podcasts are available on pilemedic.com/podcast. When you go there, there's a section that says media. You can click on that media button and then go to the podcast. There you can register for future podcasts when they're available, as well as look at the copies of all of our previously completed podcasts. And once again, I want to remind you that if you have any ideas that you would like me to cover, feel free to email me to my email mo@quakewrap.com, and we'll consider those for future topics. So with that, we've kind of come to the conclusion of this podcast. Again, you can follow me on LinkedIn if you'd like, and reminder that we have over 250 videos now on our QuakeWrap YouTube channel, video channel. So I invite you to watch some of those, and wish you a great holiday season. I hope you have a pleasant time with family and friends, however, with loved ones, and we look forward to seeing you on the next episode in 2026.